In this tutorial, I will show how to implement a simple publish-subscribe pattern with broadcast in the chemical machine. Imagine that we would have a molecule, such as pub, that is being emitted repeatedly, each time with a new value. For instance, we could implement this using a function like this. This function would have a reaction that starts when you emit the start molecule, and this reaction will go through a sequence of values. For each value, it will emit the molecule pub with that value, sleep for a given delay, and then the result would be, once you emit start, that a sequence of values is emitted on this molecule pub with a delay. So this would be an example of publishing a data set, one chunk or one data item after another. In the chemical machine, this would be modeled by emitting a certain molecule. So what we would like to do is to have a publish-subscribe mechanism so that we can attach or subscribe to this publisher, and every time a molecule pub is emitted, we would like to get some signal about it. Now, the only way to signal in the chemical machine is to emit a molecule. So let's say we would emit other molecules. So here's how we would implement a very simple example of this. If we wanted every time a pub molecule is emitted, then to emit sub1 and sub2 molecules carrying the same value, then we would write these reactions. So imagine that sub1 and sub2 already have some reactions, so when they are emitted, let's say, then these things will happen. Then we just write this one simple reaction. We consume pub, and we emit sub1 and sub2. So this simple program would run, and if we publish a sequence such as this one, then the two subscribers will get all of this data. So let me run this to demonstrate that this works. Right, so you see each of them gets each of the published values. So this is what it means to broadcast to a set of subscribers. So each subscriber gets the value that is broadcast. Now, what we would like to do is we would like to create such programs from composable building blocks. We would certainly be able to write a program like this, but this is static. We need to define upfront who is listening to what. It would be, of course, possible, but we would like to be able to compose such programs out of individual blocks that are composable. Notice, for instance, that this reaction site contains 3 reactions that are completely independent. They do not contend on any molecule that is an input molecule. Each of them has a different set of input molecules. So they could be put in separate reaction sites, which means that we could have building blocks defining these reactions separately at separate reaction sites, and then we could combine this program from pieces. So here's what we would like to have. We'd like to have some type that represents a publisher that could be started and stopped. We would like to attach a consumer to a publisher, so that each time something is published, we have some kind of reaction to it, a side effect, say. We want to be able to create a new publisher in this sense that a new molecule that will be emitted each time by subscribing to an existing publisher and maybe modifying its values. Maybe we can just keep the value unchanged as we did here. It will be very easy to add a function to compute a new value here. And we want to unsubscribe at any time. So this is now static. Once we define this, there's no way to unsubscribe. We can stop the publisher. Actually, here we can't even stop the publisher. So we want to stop the publisher. We want to unsubscribe at any time. Subscribe and unsubscribe. All of this we want to be able to do concurrently. So any number of processes should be able to subscribe and unsubscribe to a given publisher. So in our representation, let's say we have a publisher that contains a molecule pub carrying some values of type A. So let's parameterize everything by type A. Now, a typical pattern for programming the chemical machine is that we write functions that prepare new chemical reactions for us, and then we can assemble the program out of these blocks. And each function that would be used to encapsulate some piece of concurrent logic would typically take some molecules as arguments, or more precisely molecule emitters, and it will also return some molecule emitters as results. And typically the arguments would be molecules bound elsewhere, but results would be molecules bound in the scope of the function. So in this way, we should be able to bind some molecule first and then give it as argument to a function. But the function returns something that is bound inside its scope, so we cannot rebind it again. So that is a typical pattern that ensures safety in encapsulating concurrent logic. So let's try to implement this. We would need to create several sets of molecules, such as for starting, stopping the publisher, for attaching a consumer maybe, or for creating a new publisher by subscribing and unsubscribing. Every time we want to do such a thing, we need to emit some molecule, because otherwise there's no way for us to tell the chemical machine to do something concurrently. Therefore, we would need separate new molecules for each of these operations. We need a molecule for starting, a molecule for stopping, a molecule for subscribing, and a molecule for unsubscribing. Now, we could also have a molecule for attaching a consumer to a publisher if we wanted to, but I will implement it without a molecule. But for other things, we need molecules because those are going to be concurrent operations. So let's start with the publisher. Publisher needs two functions, to start and to stop. It will start emitting the molecule pub. So this molecule needs to be defined elsewhere and bound elsewhere. The molecules for starting and stopping will be defined when we create a publisher, and they will be bound inside the publisher. and so they will be returned. So that's why I have a function here that takes a pub molecule, and that molecule is bound elsewhere, and I return a publisher that has a send molecule or data molecule that contains the data that you start with, and the stop molecule. Now I made the stop molecule blocking, and I made the send data molecule carry a list of values. This is just a choice. I could do it in a different way, but I decided that's the simplest way. So you would start the publisher by emitting the molecule send data with a list of values on it, and that will already start publishing one by one with a delay, because you already made the delay there. You put already the delay into the chemistry of the publisher. So here's the code for the publisher. We define the data molecule, which will carry a list of items to be published, and the stop molecule. The data molecule by itself reacts to send the publish event or molecule. It already pattern matches on the list. If it's an empty list, this reaction won't start. This reaction will start only when the pattern match succeeds. Then we sleep, and then we emit again the molecule data with the tail of the list. So then this reaction will run again, and again publish, and again sleep. Now, the reason I did it like this is that we can now stop the whole thing by swallowing the data molecule at any time. For this, we create a second reaction that will say that stop molecule reacts with the data molecule. We don't care about the value of the data molecule. And this just sends a reply to the stop molecule and consumes the data molecule. It's not emitted again. So then nothing will be published anymore. So once we stop, we can't restart. We have to actually send a new list of items again. We can start again, but we can't resume, to be more specific. Once we stop it, we can't resume. We can restart, though. We can just start a new send data. We can emit another send data, and then this will run again. And then again we can stop then. Now if we... This is not very reliable, because if we wait until everything is done and then stop, then it will swallow the data molecule that is empty. So in that case, we would have unreliability if we stop twice, or if we start twice and we need to stop twice or something like this. Let's ignore this for now. This chemistry certainly can be improved very easily. I could, for instance, do some more molecules, or a condition that when this is an empty list, then I don't emit the data molecule, but I consume it. I could do that. But let me just keep it simple. So once we define this chemistry, we create a case class and return it. So here's how we attach a consumer or a sink to a published molecule. We just have a function that takes a published molecule and an arbitrary function from A to unit. It will be some kind of side effect. Then we just create a reaction that consumes pub and executes the side effect. Finally, let's implement the subscribe-unsubscribe mechanism. So for this, we need two new molecules, subscribe and unsubscribe. that we will emit. And these molecules have this type. In other words, the molecule emitter is a type that carries a value that is itself a molecule emitter of type A. So in this way, we can create a new molecule and put its emitter on the subscribe molecule to subscribe to a publisher. So, but to which publisher? So we need to know to which publisher we're subscribing. And for that, we create this subscribing office, so to speak, which will know to which publisher we're subscribing. And for each publisher, we need one office. So let's just make it like that for simplicity. So the make office function takes a publisher molecule and returns an office for that publisher, which has a list of subscriptions carried inside by the subs molecule. So that molecule is a list of subscriptions, which is a list of molecule emitters that are currently subscribing. The subscribe molecule and the unsubscribe molecule are going to be the externally available molecule that anyone can emit. So we define them like this. And we define the logic as a reaction site. So first of all, if the publish event comes, or the publish molecule is emitted, then it reacts with the subscription molecule. And for each molecule in the subscription list, we emit that molecule with the value x. And then we emit back the subscription molecule so that it can react with the next publish molecule. Now, the subscribe and unsubscribe functionality is implemented like this. The subscribe reacts with a subs molecule and updates its value to attach another subscriber. And the unsubscribe does a similar thing, except it removes the subscriber from the list. I did it like this for simplicity. I could have a set instead of list. I just didn't want to bother with data structures. Now, this reaction is a special syntax. You see it has no input molecules. So this is a special syntax, which means that the subscribe molecule should be statically available at the beginning of the run by the chemical machine. So this is the concept that the chemical machine supports, the so-called static molecules. These are molecules that are created at the beginning and they remain present. So each reaction must consume and emit the static molecule. If the reaction consumes a static molecule, it must also emit it. So in other words, you cannot just consume a static molecule and not emit it, and also you can't emit more than one if you didn't consume exactly as many. So the chemical machine will maintain that the number of static molecules remains constant after each reaction, like this. So this is just a mechanism for avoiding errors. You specify the initial value on the subs molecule, which is the empty subscription list. And if I forgot to emit by mistake, suppose that this code is complicated and I forgot to emit, then there will be an error. So let's test this code. So how do we use this code? We created, first of all, a publish molecule. This is the initial publisher. So we make the publisher with a delay of 100 milliseconds using this molecule. We also make an office using the same molecule. So now we have a publisher and an office for it. So now we can add some subscribers. Subscribers are molecules, so we create them, attach some consumer functions to these subscribers, so to these molecules like this. So let's just print what they got. And let's start. So we publish this data. We subscribe the first consumer. Notice that this is a non-blocking call. So this is also a non-blocking call. So all of these calls are non-blocking, except for stop. We made the stop molecule blocking, just so that when we stop, we don't have to extra make sure that everything is stopped. It's already when this call returns, then we are guaranteed the publisher has stopped, because the chemistry is such that the data is consumed here. So once the reply is sent, it means we are in this reaction, we have consumed the data molecule, nothing more would be published. That's guaranteed. So that is a very easy way for us to make sure that we wait until the stop has been successful. So we will start the publisher here, then we will subscribe the first one, wait a little bit, subscribe the second one, again wait a bit, unsubscribe the first one, again wait, then stop the publisher, and then I'll add another wait here so that we see that after stopping the publisher nothing more is published, and you see we didn't unsubscribe S2. So if anything were published after stopping the publisher, we would have seen it. So let me run this test and see if that it prints what I expect. There's an error. I wonder what happened. And the error is inside pub and subs and subscribe. Incorrect static molecule usage. Static molecule subs consumed but not emitted by reaction pubx plus subs m's going to something. Let's look at that reaction. Oh yeah, and here we have a possible live log, which is a warning. And well, that's fine. We know it's really fine. So let's see. That was this reaction, pub of x plus subs of ms going to something. And this reaction should emit subs. Indeed, I deleted it and I did not restore what I had before. This is the code I had before. So that was the mistake. That was caught early. It was caught before the code started running any reactions. It was a runtime error, but it is an early runtime error, so to speak. It was an exception generated when the reaction site was declared before actually starting to run. Alright, so now there is no error. There is a warning. Let me look at this warning a bit later. And for now, let's see what we have in terms of functionality. So the first subscriber gets the first 3 numbers. Then we attach the second subscriber. So the second subscriber now gets, together with the first one, all the numbers. And so we waited 300 milliseconds, so the first 3 were only for the first one. Then the second one got subscribed. We again waited 300 milliseconds. And then we unsubscribed the first one. So after this, it's only the second one that gets all the data. And then we stopped the publisher. And after that, nothing is printed. So that seems to be correct. Now let's take a look at the warnings. data plus stop data, and this is the reaction site. Let's find it. Now, notice this /b. So that is just a reminder that stop is a blocking molecule. This is just debugging output that is printed like that. So let's find this site. Data plus stop going to something, and data going to something. It is this site. Data going to something, data and stop going to something. Notice the order in which we wrote the reactions and the molecules is not the same as the order here in this message, because this order is actually completely immaterial. Neither the order of reactions nor the order of molecules here is in any way important for the execution. So we have warnings for this reaction site. The first warning is output molecules pub are still not bound when this reaction site is created. Indeed, that is true. What we did is we created a publisher in our test code before we attached anything to the pub molecule. This is fine. It's a warning, not an error. It's just a warning that this reaction will emit this molecule, but it's not bound to anything. Now the office actually binds it. So if we first define the office and then the publisher, then this warning should go away. Let's do that. Let's look at the second warning. Possible live lock in reaction data going to data. So what does that mean? Let's look back at that reaction. It is this reaction. Now, this reaction pattern matches on the input and then emits the same molecule again with a different value. So we don't really know what value it will emit. Now the chemical machine cannot determine what you're computing here, because that's undecidable. Now the warning means that this reaction consumes a molecule data and again emits the same molecule data, which is a possible live lock. A live lock means that you're constantly running something without actually making progress. Now, in our case, this is not so. We know that we are pattern matching on this data structure, and then we're calling data on just the tail of that structure. We know that eventually this will stop. It's not just an infinite loop emitting the data molecule back and again starting this reaction right away. It's not an infinite loop. Now, we could have easily created an infinite loop if we made incorrect code like this. Then it would be an infinite loop, just publishing the same thing over and over again forever until we stop it with this reaction. And so, since the chemical machine has no way of figuring out what we're computing and with what values we emit, it gives us this warning. What the chemical machine knows is that the left-hand side contains a pattern match. So that is indicated with this question mark. So the left-hand side of the reaction is not always matched. It knows that. And so it's a warning, not an error. It would have been an error if we just had data of x going to data of x. That would be actually an error, because that reaction is certainly just an infinite loop. But because the left-hand side is a pattern match, it won't always match. the chemical machine knows that it's a pattern match that doesn't always match, and so it tells you just a warning, not an error. So let's run this code again after changing the order in which we defined things, and see if the first warning disappears. The second warning will probably remain because it's a possible live log yes. So the first warning disappeared, the second warning remains, but that's fine. So we are reminded to look at this again and check that actually this is not just a blind infinite loop, and it isn't, so we are fine. So in this way, I have shown how to implement a simple publish-subscribe mechanism with broadcast. Now certainly this API is a little clunky and a little error-prone because we have to define the molecule, and then we have to define an office and a publisher with the same molecule. And then what if we defined the publisher with one molecule, office with another? That would be an error. So we could certainly refactor this API so that it's much faster to do things and no way to make an error. Other than that, it is a perfectly workable API that does what we need. We're able now to subscribe and to unsubscribe at will. We could, for instance, now, instead of attaching some effect to S2, we could attach an office to it, and somebody else could subscribe to S2 through an office, and so on. So that can actually be used to have an arbitrary tree of subscriptions, and that tree would be dynamic because you can always unsubscribe at runtime. So certainly a domain-specific language could be designed to make such programs much quicker and easier to write than via this kind of API, where you need to make an office separately for each molecule and define molecules separately. We can instead package all this in some case classes with some nice methods and have instead of subscribing, you could have, say, some kind of pub or S2, let's say something like this, pub. So that could be, for example, subscribe instead of doing the office. We could design a domain-specific language in a number of ways. I won't do it right now because the point of this tutorial is to illustrate the use of the chemical machine for implementing concurrent computations. So you see the entire code is this reaction site, then there's some packaging of the results, and this reaction site with some packaging of the results. And that's it. That's the entire code of publish subscribe. So this concludes the tutorial, and I encourage you to take a look at the chemical machine tutorial book. It is not part of the book, but the book contains many more examples of how to program the chemical machine for various tasks.